A few years back, Yann LeCun, one of the brightest minds of our generation, published a position paper with an ambitious title, A Path Towards Autonomous Machine Intelligence. This paper described an AI architecture called JEPA that has recently been getting some traction in real-world applications. I will not try to skim over all of the components of this architecture. Instead, I will focus our attention on the way that it leverages the concept of the world models, something that we have been discussing for some time in this podcast. Thank you for listening and subscribing. I'm Alex Chaduk, and this is AGI. Listen every Monday morning on your favorite podcast platform. JEPA stands for Joint Embedding Predictive Architecture. Very long words, but not as complicated as it sounds. Predictive architecture simply means that the design for the machine intelligence in this instance is not motivated by the generation of text, video, or other behaviors, but rather prediction of the outcomes of such behaviors before enacting them. One might say a fairly sensible thing to do for something one would call an intelligent agent. Which takes us to the first two words, joint embedding. An embedding is a transformation that takes words or images and projects them into a latent space, also called an embedding space. In a previous episode, we discussed latent spaces with an example of our own human mind space, where we go when we try to think hard about a particular problem we face in real life. In our mind space, we combine our ideas or pull them apart until we find the solution to our problem before we try to enact that solution in the real world. Compare this to what a large language model or LLM does today. An LLM takes your input, also called a prompt, transforms it into its latent space, finds the answer there, transforms it back, and then shows it to you. And then you go, whoa, this is not what I wanted. Why are you inventing facts? Or why does this dude in the picture have 3 legs? And then we try to correct the LLM through reinforcement post-training. Notice that this reinforcement happens after the LLM has already enacted the behavior that it invented in its latent space. The idea of joint embedding is to catch the AI agent one step earlier. If we embed both the training example and the desired outcome into the latent mind space of the AI model, it can see whether the behavior it intends to perform will meet our approval before it enacts that behavior in real life. This same idea of predicting the outcomes of our hypothesized actions allows us to avoid costly and irreversible outcomes that we do not want in real life. This idea of joint embedding captures the essence of self-supervised learning that JEPA tries to leverage. Like a human, an intelligent agent imagines a series of complex sequences of events and its own actions and judges whether the outcomes satisfy its objectives. One advantage of JEPA, as evident in its recent successes with video-based training, is that it allows to compress both the inputs and outcomes into more economic representations in the latent space, reducing their complexity and minimizing the computation cost. The other advantage is that there is no need to scrape, steal, or synthetically generate massive training datasets. If the AI agent can generate its own scenarios, analyze their outcomes, and learn from them. This seems to be as close as it gets to what humans actually do in their mind space. One crucial component of the JEPA architecture is the world model that allows the AI agent to predict the outcomes of its hypothesized actions. A lot more design work is required to clarify how a world model can be derived from observations. The self-supervised learning that we discussed just now is only one of the mechanisms that is required. If we want to achieve human or animal-like efficiency in construction of world models, this construction should be goal-directed, which takes us to the long-forgotten discipline of cybernetics that worked primarily on the design of goal-directed control systems. A massive advantage of building goal-directedness into the core of the AI architecture is that it will allow to integrate the ethical guidelines and objectives, or so-called alignment goals, at the start of the training, not as an afterthought as it is done in the modern-day LLMs. The other page that we can take out of the human self-supervised learning is that it seems to be rules-based. A child's play is apparently focused on the discovery of the rules that the objects in the environment follow. Yes, children show high levels of curiosity to all novel observations, but nothing beats the surprise that infants demonstrate when they see scenarios that disagree with already internalized rules like object permanence, solidity, and support that have been the landmarks of our understanding of early human learning since the Piaget studies in the early 20th century. The concept of causal rules driving the physical world will and does eventually emerge in the training of massive neural networks like the modern-day LLMs. It seems sensible to save the energy and compute by telling up front to the neural network that its learning is goal-directed discovery of the rules of the physical world rather than waiting a trillion cycles for the neural network to realize that on its own. The byproduct of keeping goals and rules explicit at the beginning of the training is that they are likely to be easier to understand for the human supervisors at the end of that training. It will be so much easier to keep emerging superintelligence aligned with the human ethical and societal goals. Probably the only place where I would disagree with LeCun's beautiful architecture is the number of allowed world models that the agent should be able to support. LeCun says it should be only one model. He does require that the model should be hierarchical to allow it to handle problems on multiple levels of abstraction and at multiple timescales. Maybe we are talking about the same thing but in different words, yet my preference is for a multitude of more loosely coupled world models. Yes, multiple world models should form a hierarchy because our brain tends to structure things into hierarchies too, and we need to understand the machine's world models to be able to trust them. My concern with a single world model is the trade-off between consistency and completeness. In an earlier episode, we touched upon this issue with an example of a consistent system of rules for municipal curbside recycling pickup that does not allow to solve the problem of recycling a recycling bin, thus making the consistent system incomplete. I would argue that we are better off with multiple world models that are internally consistent, which allows us to trust them, but which are at odds with each other. Physicists had to reconcile wave and particle representations of subatomic entities for decades without going crazy, at least not more often than your average flat earther. This is much better than a single model that creates undecidable situations or even worse, obscures its own internal inconsistency by its completeness, something that LLMs do by their design today. Maintaining multiple world models would allow an artificially intelligent scientist to explore the boundary of our understanding of the universe and promote the world models that are both supported by the empirical evidence and agree with the human-provided aesthetical guidelines like simplicity, elegance, or a smaller number of hypothesized latent variables, something that scientists colloquially call an Occam's razor. Many pundits look at the troubles that the modern-day LLMs paint themselves into and proclaim that artificial general intelligence, or AGI, is not coming. I am more optimistic because goal-directed, rule-based world models derived through self-supervised learning do show a path towards something about which we will eventually say that this is AGI.